All right, good day to everyone. I am Scott Newbern, the Chief Technology Officer at AeroVironment. Thank you for joining us for our Idea Room discussion today, where we're going to talk about autonomy at the tactical edge. Our format today, we have several speakers who will present ideas, and then we'll move to discussion and fielding some questions. We've got a great distinguished panel of speakers today, and to get this moving, I'll hand this off to Brian Clark. Brian is the Senior Fellow and Director of the Center for Defense Concepts and Technology at Hudson Institute. And really appreciate Brian joining us today. And for everyone else out there, if you haven't seen some of Brian's and the Hudson Institute work, it's really phenomenal. And I encourage you all to go out and check some of their publications. It's great stuff. But anyway, Brian is going to moderate our discussion today, and I will hand it off to him. Over to you, Brian.
Great. Thank you, Scott. Great to see you again. I appreciate the opportunity to do this event, and thank you for asking me to participate. We've got a great panel for this conversation today, and I'm really interested to hear what they have to say. And, as Scott said, we've done a lot of research in this area at Hudson, but these guys are the real experts. So to start out, we have Dr. Matt Turek. He is the Deputy Director of the Information Innovation Office at the Defense Advanced Research Projects Agency, or DARPA. He has been there for a while, and he's doing work to envision, create, and transition capabilities that give the U.S. and its allies an information advantage, so working in the information space. He's the program manager for several AI-related projects, including explainable AI, machine common sense, media forensics, and semantic forensics. So we can get into today some of the discussion about AI. And he joined DARPA from Kitware Incorporated, where he was working on computer vision technologies. So thank you very much, Matt, for being here. We also have with us Dominic Wermus, who is the Senior Professional Staff Member at the Johns Hopkins Applied Physics Laboratory, who's working with the OSD, Office of the Secretary of Defense, Chief Digital and AI Office on the Replicator program. So we'll talk about Replicator today. I'm sure as part of this conversation, probably several times. But Dominic joined Johns Hopkins from the Joint AI Center, the DoD's Joint Artificial Intelligence Center, where he had been serving as director of Autonomy project. And he came on to Johns Hopkins when Replicator was announced, where he's now leading the effort there. Prior to that, Dominic was in the submarine force. So fellow submariner, thank you for being here very much, Dominic, and we look forward to having a conversation with you about the work you're doing and autonomy in general. And then last but not least, Dr. Tim Faltmeyer is here from AeroVironment. He is the Vice President and Product Line General Manager for Learning and Active Perception Programs, so getting into computer vision and how a vehicle sees what's going on around it and understands it. His PhD research was on 2D, 3D face recognition, and he's got over a decade of experience working in the industry of computer vision and has led development of technologies for the DoD, the intelligence community, and commercial customers, most notably the Surveillance Persistent Observation and Target Recognition Program, which some of you might be familiar with. So thank you very much for being here, Dr. Faltmeyer. So with that, I want to kind of kick off the discussion with some scene setting in terms of what's happening inside the Department of Defense right now and our allies overall. So we've seen in Ukraine the explosion of autonomous systems being used on the battlefield in ways that had not been done before. Just the proliferation and the scale and the adaptability being exhibited by Ukrainian forces and their Russian adversaries has been impressive. And really highlights not just the challenge that U.S. forces and their allies might face, but also the opportunities. And I think a lot of times we tend to focus on the challenges or the threats posed by these systems and not thinking as much about how we might use them for our own purposes as part of U.S. efforts to deter aggression. So we'll talk about some of that today. But Ukraine is an example of how technologies that have been in development commercially and in the military for a while have finally made it to the front lines and are now demonstrating their effectiveness. So it's no longer a theoretical construct, where that autonomy is going to make a difference on the battlefield. It's now real life, and we can see the evidence of it. For the U.S., this sort of implies an urgency to what we need to start bringing on autonomy as a key element of the force, as opposed to being an adjunct to the traditional or crude part of the force. So we'll talk about that today, how we move beyond just either man-to-man teaming or just having a loyal wingman, but do instead think about unmanned systems and autonomous systems as a part of any kill chain and an integral part of the force. So with that, I want to turn it over to each of our panelists to give some opening remarks and sort of how they see autonomy evolving and how it's becoming a more integral element of military operations going forward, based both on what we see in the real world and also their experience in the lab. So let's start out with Dr. Turek. Over to you, Doctor.
Thanks, and it's a privilege to be here. DARPA has a unique position and perspective in the ecosystem. So DARPA was created in 1958 in response to Sputnik, with the core mission of preventing or creating strategic surprise. So we have that focus on really transformational technologies and looking hopefully over the horizon, again, to create or prevent that strategic surprise. DARPA's been investing in AI and autonomy going back to the early 60s. So again, some of the investments from DARPA have really been foundational in the field to help bring us to where we are today. The other thing that's important to understand about DARPA is that we're a research funding agency. So we don't have labs within the building in which DARPA employees are creating those technologies. Instead, we design and create research programs and then fund research performers, whether that's academia, industry, or others, to help create some of those transformational technologies. So again, DARPA is very early in the pipeline of getting things like AI and autonomy into operational use, but we've been thinking about some of these issues for several decades. And again, some of our investments have led to foundational capabilities that we take for granted now, like the ability to detect and track and fuse information to create tracks on moving targets of interest. So really happy to be here. And with that, I will turn it over to Dominic.
Hey, how's it going? Yeah, thanks for inviting me too. Pretty honored to be here. So all this autonomy stuff, it's been, especially in the past 6-9 months or so, it's very exciting. It's also what feels like a giant mess sometimes, because there were things like the announcement of Replicator, and all of a sudden, all the services, Army, Navy, Air Force, everybody, they're like, oh, so all of these projects that we've been working with this whole time, now it's really time for prime time. So it's exciting to be a part of all that. I'll give the same caveats as, I've been thinking about, where just remember, even if I've been working with the government, other folks have been doing the same thing. I'm speaking as a Johns Hopkins person today. In my previous work over at places like Jake and now CDAO. So, I've been less of like a software engineer. I've been more of like a, project manager type of person, being able to oversee the requirements, development, being able to oversee a lot of the software engineers, being able to do their kinds of work, bring it all together, like third-party autonomy software go on in existing weapons platforms. That's been pretty cool. Honestly, I'll say, the past 3 years, let's say 2020 through 2023. So anybody that was working in this space, in a sense, it kind of felt early to need. But now it's now it's suddenly shifted to the need is overdue. So again, it's a lot of fun. One more caveat that I'll add. I know that there's going to be tons of questions about, Replicator or things that are going on in the Pacific and everything else, or in Ukraine. And as much as we might all know about certain sensitive things that are going on over there, this is the public domain, and there's certain things that we'll just not be able to answer, but we'll do our best to be able to answer the audience's questions. Thanks.
Thanks, Dom. Thanks, Matt. Super excited to join this panel of experts on this topic. My background is in computer vision, and it feels kind of like it's our big time to shine. While this is an autonomy at the tactical edge kind of meeting, what we are seeing is all of the work being done
in autonomy is relying on some sort of perception, whether or not it's computer vision, whether or not it's understanding and real-time synthesis of different sensor feeds. This has really started to make us understand of what can you do with this capability and technology, and how quickly can you start to iterate now that we're starting to move a lot of the capabilities from the hardware domain to the software domain. And as we start to do those different kinds of pieces, it's really starting to open the minds and eyes of a lot of both leadership as well as employees of what can we do that can impact the nation. And so really excited to talk about that today. And with that, I'll pass it over back to Brian.
Thanks, Tim. Thank you all for those opening remarks. So I think there's the elephant in the room here, which Dominic brought up, is Replicator, partly just because I think a lot of people are interested in it as a publicly discussed effort, and I think industry is interested because there's potentially a lot of money there. So we can let's put to the side the specifics about what Replicator might be designed to do or not do, and talk about a more generic use or a more generic application. Admiral Paparo recently talked about this idea of the hellscape, where he wants to try to make the Taiwan Strait a very difficult place for operations by the Chinese Navy if they were to try to invade Taiwan. And that seems to be a pretty urgent need to help deter that kind of aggression. We've seen in Ukraine how the Ukrainians have been able to use drone boats to go attack naval forces of the Russian Black Sea Fleet. They've taken out, between a quarter and a third of the Black Sea Fleet just for using drone boats, it seems like. So it seems like there may be a potential there, but I'm interested in what each of you think about the idea of unmanned systems being able to offer the ability to address probably the top operational challenge being faced by the US Department of Defense right now, and this idea of deterring aggression against Taiwan. So I'll start with you, Matt, and then we can move on to everybody else. Thanks.
Great. Well, again, from DARPA's position in the ecosystem, there are, I think, still some foundational challenges that need to be solved here. There are very real opportunities from AI and autonomy. We've just seen probably over the last decade or so really leaps in capabilities, whether it starts with computer vision or moving into things like large language models, and more capable autonomous systems. To really get after, I think, some of the hardest DoD problems, which might involve having more freedom for autonomy to make decisions, I still think that there are foundational challenges around how do we really assess the competence of AI systems in very broad, dynamic, changing environments. How do we understand human trust in AI systems in order to allow them delegate perhaps decision-making authority to them? So those are problems, for instance, that DARPA is going after now. We have a program called In the Moment, which is about human off-the-loop decision-making in the context of battlefield triage. So what sort of attributes does an autonomous system need to have for a human to decide to delegate that sort of authority to it? That's a basic research program at DARPA right now. We're not actually building an operational system to do that, but we're using that as a setting to study some of these foundational issues. We have a broad agency announcement that just came out recently called AI Quantified. That's really looking at foundational mathematical techniques to see if we can advance the state of being able to evaluate AI systems so that, for instance, we could make formal statements, mathematically provable or verifiable statements about what an AI system is capable of doing or not capable of doing. So that's how DARPA is getting after some of these challenges, I think, that still exist to ultimately get to DoD operational needs.
Thanks, Matt. Dominic, over to you.
Yeah, when it comes to anything operational related to Replicator, it gets too sensitive. So we don't want to tie it to any specific, theater use case, anything else. However, I can suggest that what Replicator was inspired by was seeing, it's not just Ukraine. Frankly, it's all over the world. Like if you dig in the right places, you can see that this type of thing is happening. Southeast Asia, it's happening all kinds of other places. We have Navy ships in the Red Sea that There's, shaheeds getting shot at these ships every single day. And although we've been able to deter all of that, and we haven't had a single Navy ship get shot yet, which is great. It's very expensive to combat that. So we already know this is the way of the future. And I think where Replicator was inspired was I think it was taking a look at what our investments, what our portfolio was as a DoD, and then saying, how seriously are we taking these types of technologies? And saying that, well, it's kind of all over the place. And in most cases, it's really just, science and technology type stuff. It's RDT&E, research and development. And so we haven't been, operating these at the scale that we could. And it's, you compare the cost of a drone outfitted with a warhead compared to something like a missile system. And I mean, it's orders of magnitude cheaper. And it's just thinking about what are the limitations? How can we get this into, regular use cases more? And again, it's not all about kinetic stuff. You can use them for ISR. You can use them for all kinds of use cases. And I think it's just about taking this stuff more seriously, but then also figuring out, what is the state of the art today? What is it a year from now and 2 years from now, and kind of focusing on those things, figuring out if we needed to, how can we ramp up production? How can we mature the things that are close to full maturity for fielding? What are the risks that we're willing to take? I think that's what the whole discussion is about. And I will just say it is a very high priority within the Department of Defense right now. And it's one of the added benefits of it is that it has forced to the table. This whole field used to be pretty stovepiped, but now you have representatives from all across the DoD that are all coming together, sharing information about what they have, what they've done, what their intentions are, and how everybody can collaborate and work together and get to the end result faster.
Thanks, Dominic. I think we'll want to get into this idea of production and how do you get to scale, and also the idea of transition and actually fielding these systems, because that seems to be a gap right now, is who actually owns these systems, operates them, sustains them, et cetera, because right now we just can't hand them off and give them to somebody. There's no person to operate them right now. Tim, what do you think?
I completely agree with a lot of Dominic's kind of thoughts and points. And almost to address some that Matt made earlier, one of the big distinctions that we get countered a lot of times with is AI. What really is AI in this realm? And that's always one of my kind of big talking points when I talk to different customers is there are AI systems, there's artificial intelligence systems, but really it's not a big scary thing. It's made up of individual components and individual mission sets that are understood. And in my case, I work a lot in perception. So it's how do we get the computer to see something based on a requirement that a customer may have. That something may then feed into an autonomy algorithm that would then have a course of action or do a set of things. And so a lot of the times the problem really becomes, what are you really trying to test? So for things like explainable AI, is the goal to understand what the perception sees and why it sees it? Is the goal to understand why the autonomy algorithm decided to have the plane take a left instead of a right? Is it the goal to understand, did the mission succeed or fail based on all of the things that made up that mission? And a lot of the work that we are doing here is that education, both just for customers as well as for the community, of this is not a big scary thing. This is a bunch of really well thought out individual components that individually, if evaluated, could say exactly what they're doing. And then as you start adding them on again and again, you can actually understand, I have very high probability, I understand what's going to happen when I run this model with this autonomy algorithm in this environment. And so that's one of the big talking points that we like to really just make sure it's understood. It's AI is this big scary term that literally everybody is using today. If you break it up into the core components of what you're trying to do with it, it is very understandable.
Yeah, that's a really good point, Tim. And I think that's one thing we want to try to dig into here as we talk about autonomy and how do you evolve it. So one thing that the discussion you just brought up raises to me is the role of conop development or use case development in concert with the development of autonomous behaviors in a system. And I think sometimes in the technology side, we talk about the challenges of reaching a certain level of automation inside of a system, whether it's the computer vision element or the guidance and control element, or it's the decision-making command and control part of it. But there's also a role for conops. I mean, clearly in Ukraine, they're developing use cases that take advantage of the pretty modest level of automation that's available in the systems they have. So the operator can have a role in here, making a system that is not quite where we'd want it to be in terms of automation, but viable as a useful military system. So how do you envision, or how do you work today, or how do you envision working in the future with operators to come up with that marriage between the automation and the conops that gives you a minimum viable product that can be delivered out to the field right away, as opposed to something that requires more S&T before it's before it becomes a viable system? So I'll start with you, Matt.
Sure. I guess I'll pull an example from that in the moment program. And I agree with you that the use cases can be critically important, both for the development of an AI system, right? You want to be focused on the right sort of problems, and then also for the evaluation or acceptance testing of an AI system, because you want to do that in the context of something like a use case. On that in the moment program, one of the interesting aspects in that area is that it's not unusual in battlefield medicine for there to not be right answers. There's multiple courses of action. All of those courses of action may have downsides to them. They may be fraught. There may be no good answer there. Makes it very challenging to assess an AI system based on the outcome. So we've been focused on other dimensions, alignment with attributes of humans that lead to trust. And in those settings, we are developing test settings, test scenarios, vetted with medical decision makers from the DoD, whether that is trauma doctors or whether that is medics, to try and create highly realistic scenarios. We're using those scenarios actually to evaluate humans, to try and capture some of those attributes of humans. What is their decision-making process like? Do they continue to seek information, or once they find a decision that they think is good enough, do they move forward? That's maximizing versus satisficing tendencies. But we're using that development of scenarios, that development of conops, to come up with very concrete ways to test the humans, and then eventually to use that to help evaluate the AI systems. So again, that idea of having those use cases or conops, I think, is critically important.
Thanks, Matt. Yeah, so Dominic, you're probably doing some of this work right now in relation to Replicator, but just in terms of the process, how do you envision this working going forward in a way that's repeatable, sustainable, so it's not just a pickup game every time we want to come up with a new autonomous system. We actually have a way of working through the use case and figuring out what's good enough on the technology side to support the mission that we're trying to accomplish.
Yeah, sure. And I'll say, like, from the CDAO side of the house, there's still plenty of autonomy programs out there across the DoD that are not considered Replicator. And so, CDAO, I'll just say that, they care about all of these things being successful. So when you talk about the T&E point of view, so I think part of what CDAO is supposed to be responsible for is making sure that people understand, what are the approaches? Do you really want to dig in and pick into every single component, especially if it's a very complicated system? There are simple autonomous systems that will just have, something like, I don't know, it could be something like a radar receiver, and then just something like a very simple auto router that drives a series of waypoints and then makes its way over to a place. You can have exquisite ones that have like hundreds of different types of functions, that have awareness of where they're at now, where they've been in the past, what did they see, the ability to adapt live to their environment, all these sorts of things. When you try to dig in to every single piece and component, it gets overwhelming. So the way that, for example, in prior JAIC projects, Joint Artificial Intelligence Center ones, the systems were honestly so complicated that we just said, hey, ultimately, this is what we care about. We want to task the system to be able to take off from here, go over here, find a target of interest, and report on it. That's it. So then from a T&E perspective, all we really cared about was, this is very similar to how like Navy minesweepers are assessed. So give it a box, say something like 10 by 10 square miles, and just say, of all the targets that were in there, how many did you find? How many did you miss? How many did you misclassify? How long did the whole process take? Yes, we still do care about how well different sensors performed, how long the platform was able to survive in adverse weather. How did the computer vision models perform? All these sorts of things. And they can be used to help diagnose the overall system, but try not to make it too complicated, especially if you've got a small test team. So making sure that we have those lessons learned, we have these things documented, and that we have the ability to teach other program offices to be able to do this for themselves. That's really the ultimate goal. So, try to narrow it down to what is the thing that you really want out of this? And then try not to overwhelm yourself with too much detail. Understand at least the basics of the system, but really leave it to the engineers, to the professional experts to be able to diagnose and be able to do the rest. So again, I think CDAO specifically, among its many roles, it's responsible for things like test and evaluation policy, and at least being able to teach other folks, other program offices that are trying to do this for themselves, what is the right way to do this, or at least what's a good place to start.
Thanks, Dominic. What that makes me think is of this difference between test and evaluation as a formal process for putting something into the field and going to full rate production versus the evaluation that you need in order to field it as an initial operational capability. So normally we think of those as being extremely different, right? So you might get it out in the field as maybe even emergency prototype capability, but then at some point someone's got to go and do T&E that's going to take years to really check all the blocks for satisfying the original intent of the system. But with these software-defined capabilities, do you find that the ability to go quickly from initial capability fielding to full test and evaluation is accelerated because you're able to do a lot of this digitally as opposed to having to do it all out in real world open air testing?
Yeah, so for any of these types of systems, it really depends on, so who is the program office that is supplying the capability? And then what is the demand signal from warfighters? And there has to be a balance between both. So ultimately, the program office is going to be responsible for the risk taken. And I've seen where the operational community is willing to take plenty of risk. It doesn't mean don't do any testing. It just means hey, we're just going to do the following series of field tests. We want to get as close to realistic as possible. That there's two types. There's developmental test, which is, does it work? And then there's operational test, which is it useful? So I've seen for even some pretty exquisite systems that hey, people wanted to see this out in the field, some kind of prototype, some kind of demonstration relatively soon. And again, it doesn't mean that no testing was done. It just means that they checked the blocks that they knew needed to be checked off. And then once it was considered good enough, here's the failure modes that we're aware of. We'll train the operators on, what to do in these types of situations. Let's get out there and go operate in the real world. And then we'll take that back and then continue the whole developmental test and operational test and just keep iterating on that. And this is especially important for autonomous systems just because these things are, in all practical sense, they're living. You need to keep iterating on the software and the capability over and over and over again, especially as you adapt to new biomes, new targets, new areas of operation, that sort of thing.
Thanks, Dominic. So Tim, you've worked in the civilian world doing this for customers. So I assume that you have to work pretty closely with customers to make sure that the product is going to deliver what they're looking for, and they're not as interested in the perfect technological solution as much as they're interested in something that solves their use case. So, is that a model that we might be able to apply here to the military application?
Absolutely. So it's education is what it is for the most part. A lot of times we'll come in with requirements from a customer, and the requirements were created by someone who may have never understood what is possible in terms of computer vision or AI or those kind of components. And what we end up doing is having this be a collaborative process. So rather than it being an edict coming from on high that this is what the system should do, we help the customer understand this is what technology can provide you today. These are areas that we think that we can work with folks like DARPA or CDAO to expand, to potentially get to those further rings that we can't reach now. But these are things that we can absolutely do to change the fight today. And really that understanding of how do you both work in those constraints, but more importantly, as Dom said, iterate as absolutely quickly as possible. If you think of the way that DT and OTs used to work, where you have one time a year that you get your chance to go and test it, and 3 years later, that system is fielded. The real aspect of it is today's mission, you have a DT and OT before it. Then you have to be able to run that whole process, take the feedback that you got from that mission, and on the next day, you should be learning from all of those responses. And if we can't build a process that is able to do it at that pace, I think it's the downside of the process, not the capability. Because I know from a technology standpoint, we can move that quickly.
Yeah, thanks, Tim. Definitely, and I think that's one of the probably challenges for Replicators coming up with this process that we hopefully can apply in future use cases. So it's not just a unique effort to Replicator. We've talked about computer vision several times. Obviously, you've all worked in computer vision to varying degrees. I think one thing we've seen in Ukraine in particular is the effective use of decoys. What's happening on the battlefield is, because first-person view drones are becoming the kind of ubiquitous go-to battlefield sensor, there's been a big effort to try to use decoys to deceive those drones, because maybe their cameras aren't that great or their computer vision isn't that great, and you end up with a information competition over who can deceive the other side better. And the Ukrainian troops have been pretty good at this decoy operation, at least thus far. I want to talk a little bit about that and see what you guys think in terms of where computer vision is today and where it might go in the future. And how can we apply our understanding of computer vision for these drones and unmanned systems to our own decoying efforts? Because we're going to face this same threat. The Ukrainians can do it. Certainly any opponent the US will go up against can do the same thing. So we should think about, how do we deceive these kinds of capabilities if we have to on the battlefield? So Matt, to start with you, how do we try to win that aspect of the information competition, the sensing, counter-sensing competition, if you will? And where are we with computer vision today in getting an edge?
Yeah, I mean, obviously there's traditional techniques for coming up with decoys, right? You could have things that appear to be vehicles that they're not. They look that way to humans. So for instance, something that might look like a Russian tank, but is actually, not actually a physical vehicle. Maybe it's just something that's printed and assembled in the field. I think one of the interesting trends that we might see longer term is using things like adversarial AI techniques to attack some of the automated target recognition algorithms. So there's pretty well-established work in the academic community that, at least in academic settings, that you can use these attacks and understanding of how those algorithms were developed, the data sets that were used to develop them, to come up with unique patterns that might cause those algorithms to fail in unexpected ways. So again, I'm unaware of that actually being used from an operational perspective, but from a research perspective, there's foundations there that could be exploited. DARPA's had a defensive program in this space to try and build much more robust machine learning algorithms that can defend against those sorts of attacks. And some of the foundational approaches to that have been provided as open source. So you can go to look at the adversarial robustness toolkit, which is out there again on GitHub. And that's a unique resource that might help folks in the defense industrial base build machine learning algorithms that are robust to those future attempts at deception.
Thanks, Matt. One follow-up on that is, to what degree is this a sensor limitation versus a software limitation? Are we better sensors? Will they help with this very much? Or is this really fundamentally about how good is your algorithm for being able to understand what it's looking at?
There's multiple ways that those adversarial attacks can be carried out. Some of them imply, obviously, vulnerabilities that you don't want to have, like the adversary's ability to insert noise patterns in your sensor data or to poison your training data. So those are really like cybersecurity and software issues. But there are attacks that, if you have some information about how that machine learning algorithm was trained, what sort of training data, that the algorithm itself really can be attacked. So that's different than just a software issue. It's different than just a sensor issue. It is actually an issue around properties of these machine learning algorithms.
A great point. Thank you very much, Matt. So Dominic, in your work, how are you approaching this question of how do you win the sensing counter-sensing competition? Because we're likely to face this in any military application of unmanned systems going forward, because it's in the mix now.
Right. Yeah. So, I mean, this is a constant topic of conversation. So we know it's going to be a problem. So, it's we'll try to come up with one capability, an adversary will come with a counter capability, and we'll try to overcome that, and so on and so forth. And people are trying to roadmap exactly what that's going to look like. And so we want to be, playing a game of chess where we're looking 5-7 steps ahead or more. So your original question was about decoys. My piece is on this, that decoys are a problem in the military no matter what. So how much does AI change things? I mean, so far, may or may not change a lot. So you still need to be able to have human reviewers. They try to look at other things than just, what's in the camera. They're trying to understand what's the context of what's going on. And that's still a very largely exploratory space. I'm not saying it's not being used, but there are major investments taking place there. One of the best ways to overcome something like decoys, although it's not foolproof, is to be able to have a diversity of sensors. So it's not necessarily having better, more powerful cameras. Yes, it can help. But for example, having full motion video camera, EO/IR, something like that, plus synthetic aperture radar, plus radar sensing capabilities, plus there's plenty of kinds of sensors out there in the inventory. But, all these different platforms out there have swap constraints. These sensors are expensive. In some cases, the sensors themselves are more expensive than the actual platform. So there's caution there. There were discussions here about things like adversarial AI. I'll say, obviously people know about things like patch attacks. Throw on a sticker onto something and all of a sudden the computer vision algorithm can't see it anymore. That gets into the fine nuances of what type of computer vision algorithm are you using? And so people are trying to figure out that piece too. Should we change our approach? Anybody that's relying on something like computer vision alone, that stuff can be defeated pretty easily. You need a whole bunch of diverse set of technologies to be able to overcome that. And not all of them are based off of AI. I don't want to sit here and bore you guys with different examples, but just know that this is a very active topic of conversation. And maybe one thing that I'll add to that too is saying that we've worked with different types of AI cyber red teams before, and I was surprised that they cared less about defeating the live AI system in action. They were more interested in actually being able to get into the development networks, see how they could get into the software, get into the AI training data. How can they poison things? How can they do that sort of thing? I was pretty surprised by that whole process.
Thanks, Dominic. That's very interesting. So it takes you to a different, basically, attack vector, than going after the algorithm itself. You got to go back to the supply chain, if you will, for that capability. Tim, this is your area of expertise. So where are we with regard to computer vision for autonomous systems? And what's the art of the possible in terms of the sensing counter sensing competition, and how does the U.S. and its allies get an advantage there?
Yeah, so I think it's actually a multi-pronged approach. The first one, if you think back World War II, they had inflatables that they would be seen, and the human was going over top of it, and the human was not able to tell that those were in fact decoys. And that's what I envision will occur. There will be times that whatever the crazy decoy for the cat and mouse game is for the day, that will work. And this is back where it comes to a software-based system, that once we realize it was a decoy, are we able to change our software faster than the decoy and the next decoy can be created? And at what cost? I think if you understand both those, you have a jobs program for quite some time, which is very good for my business and industry. The other aspect that is, very strongly related to this, it is surprising in industry how many people leverage the same core software. So YOLO is an example of an open source algorithm that it seems to be in vogue with just about everyone who is doing something and wants to be able to show computer vision doing a capability on day one. They download from GitHub, they run a model that has a bunch of default classes, and then they're off and cooking. The challenge with that is that the more people that use that architecture and that system, especially without understanding how it was constructed or created, creates a vulnerability set that makes it very advantageous for an adversary to specifically target that architecture. This is kind of back to the whole Windows and Mac with virus. Windows was a huge source of viruses because there were so many users of it. And for the most part, Mac in the way that was constructed was kind of left alone. And obviously, as times change, that becomes the vector. And so the more that everyone can understand what they are using as technologies and not just pulling it off the shelf and claiming its success, that's really the key.
Thanks, Tim. A really good point about the whole software supply chain and the vulnerabilities that might exist there. I want to talk a little bit more about sort of the applications of autonomous systems on the battlefield, since we're focusing on autonomy at the tactical edge. So it seems like one of the big changes that's happened since the war on terrorism kind of introduced the Reaper and the Predator into the military as new or like semi-autonomous unmanned systems to today is the fact that now we've got large numbers of autonomous systems operating on the battlefield, a lot of ways collaborating with each other, in some cases collaborating with crewed platforms. And certainly that's a vision going forward. There's going to be a lot more collaboration. But it seems like the difference is we see a scale and the introduction of uncrewed systems all across the kill chain, and different components of it. So now we have to think about, how do I compose these systems of systems? How do I build a kill chain? And then how do I take advantage of the versatility of a swarm of unmanned systems to be able to deliver a bunch of different effects, in concert or separately? And so one thing I'm interested in is, and I think the group might be interested in listening, is how do we manage these systems? How do we do command and control in a way that gives us a decision-making advantage? Because it seems like one thing we can do is really employ groups of unmanned systems in many different ways, which could give an opponent many different dilemmas to have to face and prepare for. But how do we actually take advantage of that and not just use these as sort of a homogeneous swarm that's just dumb mass, or use them like a Predator, where it's a single thing doing a single mission? So Matt, how are we trying to get decision-making advantage by using groups of uncrewed systems and autonomous systems together in new ways?
Yeah, well, one of the things that I'll talk about there, and again, more forward-looking, but like, how do we have fluent human native interactions with these sorts of systems or combinations of systems? Trying to handle the cognitive load of dealing with large numbers of systems and multiple tasks and stuff like that could be very challenging. If you think about maybe not UAV swarms, but if you think about multiple ground robots with a small squad in an actual combat scenario, that squad needs to be able to maintain situational awareness. They can't spend a lot of time paying attention to what the unmanned ground vehicles are doing. So how do we get them to a place where they can be heads up, where they can be hands free? They don't have to sort of be heads down on a laptop or some sophisticated user interface. And so that's probably going to require just, again, more fluent interactive teaming. Maybe via dialogue is one way to do that. That's how humans interact with their squad mates now. But that's going to require not just speech recognition, but understanding the context around, so that the speech can be very terse and very directed in high pressure settings and scenarios. And of course, needs to be able to handle unpacking, very burdened DoD words that might expand to a lot of information in a particular context. Those, I think, are still challenges that AI systems aren't ready to address. But that would really provide us some operational advantages in some of those challenging scenarios.
Thanks, Matt. And one thing I wanted to ask you about is the balance between a system that operators are familiar with, like an ATAC, or we've talked to folks that operate the FAD-C2 system that does counter UAS missions. So they're used to how it works, but it can be cumbersome to operate, versus a new system that might incorporate features like dialogue or other tools to be able to more quickly get your meaning across to the systems and then be able to get back feedback from them. How do you balance the familiarity versus novelty that might offer a new way of doing it?
Yeah, that's a great question. I mean, maybe it again goes back to having capabilities that are ultimately intuitive for a human to use, and then you're going to need to rely on training processes to help bring people up to speed and ultimately build trust in those sorts of interfaces, so that they're willing to use both that interface and the capability in fraught settings.
Thanks. Dominic, I think one aspect of this that's obviously on people's minds right now is, how do you make it so that the command and control or decision support system that you're going to use to manage your group of uncrewed vehicles or autonomous systems, how do you ensure that it is open and be able to have a bunch of different vehicles plug and play into that command and control system? And give you the performance that you're looking for, so they're not just having the most simple direction provided, but they can actually participate in a collaborative way. How do you create that kind of software ecosystem within your group of uncrewed systems?
Yeah, I mean, when it comes to that topic, I love this topic also because of, there's a technical aspect, but there's also a political aspect to it. So I want to say, from a technical perspective, like, it's already been done and proven over multiple times. So to get these kinds of uncrewed systems to communicate and collaborate with each other, so you need matching radios or matching communication systems. You need the right protocols in place. And so, for example, like in the Jake days, actually the first kind of collaborative autonomy framework that we used actually came from DARPA. So it was called DARPA Code, Collaborative Operations in Denied Environments. I think that thing got started in 2012. DARPA made huge headway with that. I think it transitioned over to SCO, Strategic Capabilities Office, and now large chunks of the Navy have said, or at least for NAVAIR, Naval Air Forces, they've said this is the standardized framework we're going to use. Nothing wrong with that at all. Other services, for example, like the Air Force or even other parts of the Navy may say, actually, we have this going on. We're going to use this instead. In a lot of cases, these collaborative autonomy frameworks are kind of derivatives from each other. Many originated from DARPA code. So getting them to talk to each other may not be technically that hard. The hard part is getting all these different services, program offices, everybody else to agree with each other that this is going to be the standard. At some point, somebody up from the Office of Secretary of Defense probably is going to have to say, all right, guys, enough is enough. This is the standard. But anybody who chooses to do that has to do so very cautiously, because we've seen it many times where the Pentagon says, all right, enough is enough. We're going to use this. They lock down the standard, and it is not something that's really can be iterated upon. It's frozen and it can't adapt to new technology as it changes. So this is a balance. This is a very serious point of discussion between between CDAO, between DIU, between all kinds of other places. And so I'll just say that the discussions are being had. Technical perspective, not concerned at all, but just the policy perspective. We do have to get to that point at some time or another. I'll say the activities at a minimum that are going on right now are, again, everybody coming to the table and saying, this is what I've got, this is how mature it is. This is what I've got, this is what I plan to use, et cetera, and at least listing it off and seeing what would the technical barriers be if we set a certain policy that we will have this one standard to rule them all. That is the state of the discussion right now.
Thanks, Dominic. Tim, the aspect of that I think is interesting that you could certainly shed some light on is the role of decision support systems inside these command and control tools. How do we enable an operator to get the most out of the group of uncrewed systems that he has available to him? So not just throwing them at a target and just trying to use mass to overwhelm the target, but maybe coming up with conops or tactics that are going to be more effective in defeating a particular target. And then also kind of thinking ahead to what are the next steps, what are my next plays down the road. To what degree are we able to think about using machine learning tools or AI-enabled tools to help operators think through the best tactics to employ with their unmanned systems? And then as we go from an era where it's just all about mass to an era where it's about mass and some kind of creativity as well.
Yeah, so I think that the answer to that first part of the question is it's going to come down to how would a human do it today? So if you really look at it from a computer vision perspective, if you had a person that was able to be in the cockpit of the very small UAV, what kinds of things, given the Mark II eyeball, could they produce from that data? And if we can make those into discrete components, then those become building blocks that the autonomy algorithms can then go forth and do different mission sets. The real key, though, is kind of touching back on to what Dom was saying. It's about data sharing. And I think that there are right ways to do that. And I think there are ways fraught with peril. I had a really great discussion with a guy named Chris Murphy, who was over at DIU, regarding some of the ideas that they have. Rather than creating a big centralized framework that is trying to solve world hunger, the focus is on everyone having their own platforms and having the data that comes out of those platforms be able to be translated and understood in a common language. If you can take everyone else's products as they exist today and get it to a format that can be understood and reasoned over, then whoever decides to bring that framework, be it a government solution, be it a contractor, or anything in between, everyone has access to the same Legos. The building blocks are there. The capabilities of a super intelligent and fantastically expensive and smart system are available. And maybe for a UAS that was built in the 90s, maybe all it can do is one kind of mission set, but understanding what that is in a reusable fashion so that those frameworks can make use of the capabilities for each one of them. And most importantly, and again, this is selfishly, share the perception that is going across each one of them. That is what's going to be that big jump. In AV, we have a whole bunch of different products from Jump 20 to Pumas to Switchblades. And historically, missions have been constructed for each system by themselves. You have a Jump 20 mission, which is different than a Switchblade mission, which is different from a Puma mission. But so frequently, you actually see the same assets on the battlefield in the same areas at the same time. And maybe even other assets, like an MQ-9 that could be overhead, or a Global Hawk. And in each one of those cases, the key is how do you take the perception that is coming from those other assets that may have a better vantage point, or may have had a longer persistence, and help inform what you are trying to do on each of the different echelon levels. And the more that we can automate that process, so it's not a PowerPoint slide that gets written and briefed to someone at the end of the mission, but it's an interchange, that's where I see CDAO and OSD really stepping in and saying, there has to be this pipeline of data that can flow across these different program offices, across these different services, so that whoever needs them can make use of them around the different mission sets.
Thanks, Tim. One thing that also makes me think about is one of the challenges faced in Ukraine right now by uncrewed systems is navigation warfare. So GPS jamming, GLONASS jamming, jamming of satellite navigation in general, as well as interruption of communication links. So when you try to shift to your first-person view video being the source of navigation information, you don't get it because I can't send a radio signal to my UAV anymore. Can new approaches to computer vision try to address those challenges in navigation warfare?
Absolutely. I mean, when I just was watching a show on Apple TV, I think, Masters of Air. So World War II bomber pilots able to fly hundreds and hundreds and hundreds of miles well before the age of GPS. They had a map. They could do so at day and night. And those capabilities existed for people who were in the cockpit to do those and make those decisions. And for the most part, and again, there are obviously exceptions, but for the most part, they were able to do that traversal and get from point A to point B without the use of GPS. To me, if we could do it 80 years ago, it's just a matter of automation and breaking down that problem into the core components. And back then, they didn't have the advantages that we have of different radar techniques or different infrared techniques. All they had was their eyes that could look out the side of the window and see where they were when they were. And so where I see a lot of that technology going is oddly enough what we've already done, and just doing so in a more automated fashion.
Thanks, Tim. One of the other things from Ukraine that I wanted to make sure we addressed before we close here is that the importance of adaptability and how you can send material downrange and have all the hopes for how it's going to be employed, and then efforts like navigation warfare, just troop dispositions, other challenges in electronic warfare, make it so that your conops don't work anymore. How can we enable autonomous systems to have the kind of versatility that a human operated system would have? We kind of rely on operators to take the initiative and try to accomplish commander's intent, even when they lose communications with home. So Matt, how are we going to need to enable this kind of next generation of autonomous systems to be able to adapt at the tactical edge, or allow operators to adapt them in the field?
Yeah, I mean, that's an important question. Again, this is a place where DARPA has made some foundational investments. We had our machine common sense program, which was really focused on, can we develop new AI algorithms that demonstrate the learning flexibility that human infants have. Some of the results from that program actually has led to new foundational algorithms for robotics. So being able to train robotic systems completely in a simulation environment and then being able to quickly deploy them in real world settings. This is particularly around ability to traverse new and unusual terrain that they weren't even trained for in a simulation environment. So it's not even training specifically for a particular environment, but just training in general for the real world. That was a really interesting result from that machine common sense program. In terms of how humans might help maintain these sorts of systems, we have another program, perceptually enabled task guidance. Think about that as a little AI angel on your shoulder that knows what you're trying to accomplish, can perceive what you're doing, and can prompt you if you miss a step or you make a mistake. Super useful, in time-pressured situations, or when people are fatigued or you're trying to upskill someone who hasn't done a task before. That can potentially help on the maintenance side.
Thanks, Matt. Those are great examples. So one thing I was going to ask you, Dominic, we had talked about this idea of a software ecosystem and a framework for command and control and managing autonomous systems. But how do we enable this kind of adaptation at the edge, by operators, which might include software updates. You see that happening in Ukraine now, where operators are having to update the software in the field for their autonomous systems or for their command and control systems even. How do we enable that kind of software development in the field? And do we need a different pipeline for that compared to what we might use for the enterprise systems that we're using, to kind of manage the rest of the force?
Yeah, sure. This is another one that people are talking about this topic every single day, because you think about something like, the Marine Corps' approach to the Pacific. So, the whole new force design and, the expectation that, forces will be out there, for example, in the jungles of the Philippines, and may have no connectivity back to stateside systems, no matter what. So then if they're expected to use autonomous systems, how are they going to be the ones when they're, potentially not able to get any help from stateside? How are they going to, sustain and improve and do all these different things? So there's a lot to it. I will say that on one hand, there's a lot of investment being made in being able to really have that resilient connectivity. Probably shouldn't go into too many specifics there, but people are trying to keep those options open. Also, to that point, I've seen plenty of different projects emphasize like edge retraining or edge software maintenance to a very high degree. And so the goal is ultimately to have uniformed folks, sometimes very, very young folks who are not software engineers at all, be able to do this stuff themselves. And to be honest, like some of those experiments have proven pretty useful. I wouldn't expect them to build something new from scratch, but they can be shown the basics of how to troubleshoot something from a software engineering perspective, and it's not bad. I also think that's some of the way the future. But I think we got to take advantage of both. Like we should assume that communications back stateside will be cut, but when it's there, exploit it, take advantage of it. Be able to get folks from stateside, engineers, whomever, to get these folks together on a phone and say, hey, this is what you're facing, do this, do this, do this. Or let me push you a software update over here. This should fix your problems. But people, in today's operating environments have to be able to fend for themselves. And I'm just going to say I've seen a lot of experimentation to date, especially Marine Corps side and Navy side, that they have already shown that this can work. And so there's a lot of promise there, I think.
Thanks, Dominic. So Tim, the one thing I wanted to ask you about related to this was how much autonomy do we need to have, or can we get on platform on some of these smaller autonomous systems versus what might need to be drawn from some kind of computing that's available either remotely or locally? Do these systems need to have some kind of backup computing power to be able to really fully achieve the kinds of computer vision or the kind of autonomous behaviors that we're hoping for? Or is this something we can pretty much push to be completely on platform?
So everything that we're working on at AV today is focusing on getting that processing as absolutely close to the edge as possible. What we're seeing is if you had to rely on getting that video stream back, one, you're really challenged when it comes to comms, because now that is the limiting factor for what you can actually get down to the operator. But two, the more you can do on board, the faster the response time, and more interestingly, the more you can actually do with the platform itself. So if you think of it from the perspective of humans watching a Puma feed, and the Puma feed's coming down, and they're wanting to control the sensor, or they're wanting to track a vehicle or track an object, that amount of time takes delays and latency between when they can select what they want to track to getting the bird to move the sensor to go and do the object. And that's with one Puma and one operator. Imagine now if you have 10 Pumas and one operator covering an entire island. What you want is for the dynamic to change from the Puma being the video source for a human to a Puma acting upon that commander's intent. So some of the work that Matt was talking about from DARPA, being able to display or to tell actions of what you want, and the system goes off and figures that out. The key enabler to all of that is having the ability to do that processing on board so that it is its own independent and self-sufficient capability. And to what Dom said, when times are good and we have comms, we'll get data back. We'll get pictures, we'll get video. But when it's not, it still should be able to execute its mission as per the commander's intent.
Thanks, Tim. So I think that's a great place to end our discussion. Autonomy at the edge is a real thing. We're seeing it happening in Ukraine today. We're seeing it happen even in the Middle East today. We need to figure out now how to deliver it more quickly to U.S. warfighters and allied warfighters to be able to take advantage of this technology ourselves, while at the same time, thinking how we're going to defend against it and counter it. But I want to thank our guests today. We really appreciate the time that you've taken to help kind of enlighten us about the state of autonomy and where we might go going forward as some of these new efforts like Replicator take off. So Dr. Matt Turek from DARPA I2O, Dominic Wermus from Johns Hopkins University Applied Physics Laboratory, and Dr. Tim Faltmeyer from AeroVironment. Thank you very much all for being here today. And with that, I'm going to turn it back over to Scott Newbern to close us out. Thank you very much, Scott.
Okay, thanks, Brian. And again, thanks to our panelists and of course, Brian for not only moderating, but also providing his knowledge, experience, and insights. That was awesome. So thank you for our attendees today as well. And we look forward to having you back at our next event. And we'll see you then. Thank you.